Welcome back to the sequel, Modeling Dissolved Oxygen 2, the spreadsheet. So let's launch right into this. We're just going to put these differential equations into a spreadsheet, and by the finite difference method, we'll look at the evolution of oxygen across time in this stream. If you want to implement this in a programming language, be my guest. That is definitely how any scientist would do it, and that is would be my preferred method as well. But I can't assume that everyone knows a programming language, so we're going to go forward and do this in a spreadsheet in this class. And so what I've done to make things easy for y'all is I have prepared a spreadsheet in advance that has blanks for all the stuff that you'll need to either enter in or calculate. So we can just kind of fill this out together. You've been provided the link for this, and we'll work through this problem together. So let's launch right into it. These values are things that you can choose, or time step, in hours. Let's say we're modeling this over 5 days, so a half-hour time step doesn't seem unreasonable. We'll just put it in as 0.5. The stream depth, you'll recall we set in the previous lecture, we said that the depth was 0.5 meters. So we'll put this here. Our river temperature. The river temperature that we said was 12 degrees Celsius, and we need to convert that to Kelvin, so add 273, and we have a temperature of 285. I do not want to autofill that. And our initial oxygen concentration, I said I would give this to you, and I will give it to you. It's going to be 0.000345. Okay, good. Good enough. So this is the concentration of oxygen at midnight at the beginning of our model, times 0. Okay, now the next step that we said we needed to do was to calculate the equilibrium concentration of oxygen so that we can use this equilibrium concentration in this kinetic formula shown here. You'll recall that that is an important part of this formula. So to do that, we said we're going to first use Van Hoff's equation to calculate the equilibrium constant at the temperature of our stream, and then just use Henry's law with that equilibrium constant to calculate the equilibrium concentration of oxygen. Okay, so we'll just say the partial pressure of oxygen is 0.21, atmosphere is 21% oxygen, at sea level your atmospheric pressure is 1 bar approximately, and so just move on from there. Now we can use the Van Hoff equation to calculate the Henry's law constant of oxygen at the river's temperature, which we said was 285. And so again, what we need to do is rearrange this equation here so that just Kh at temperature 2 is on one side. And so what we're going to do is just exponentiate both sides or raise e to each of these, and then multiply through by Kh at temperature 1. So to implement that, we'll go back to our spreadsheet, and we'll say Henry's law constant at the river temperature, 285, is equal to the Henry's law constant at 298, which is stored in cell B9, multiplied by e raised to, and to raise e to something, you put exp in a spreadsheet. That's the function that raises e to something. The enthalpy of reaction of oxygen gas dissolving into aqueous solution, and that enthalpy of reaction, this is also called the enthalpy of solution when you're dealing with dissolution of gases. The enthalpy of solution is 14.13 divided by R, the gas constant. And actually, I'm going to put parentheses around all these things. And 0.00831445. Hopefully you have that number memorized by now. So this is the enthalpy of solution over the gas constant, multiplied by 1 divided by the target temperature, which is 285 Kelvin. And that is, did I name that? I think I did. No, I didn't, but that's fine. B5 minus 1 divided by 298. Close that parentheses, close that parentheses. Great. That is our Henry's law constant for the temperature of the water, 285 degrees Kelvin. And so now to calculate the equilibrium concentration of oxygen at that given temperature, we simply multiply this number by the partial pressure of oxygen in the atmosphere. So I'm going to say B12 multiplied by B10. And here is our molar concentration of oxygen at equilibrium for any water at this temperature. So first part of the equation solved. Okay, now we're going to fill out some other parameters as we go along here. The next parameter that we want to put in is the gas exchange rate constant. And the gas exchange rate constant was given in the problem that we defined before. And this was 1.1 meters per hour. And you can read a little explanation over here about why this is in meters per hour. That might not make any sense to you, but don't stress about it. And good. And here I just reminded you of the differential equation that we're going to be using. The gas exchange constant multiplied by the difference between the equilibrium concentration and the actual concentration multiplied by your time step is equal to your flux. And so this again is a flux in moles per meter squared. And so to get to concentration, we just need to multiply the flux divided by depth. Sorry, not multiply, but divide by depth. The reason we're just dividing by depth is that we said that the top of the unit that we're looking at is 1 meter squared on each side. So dividing by depth is essentially dividing by the volume. Okay, so to do that, we're going to use this depth here. We're not going to enter this on this sheet, but just to remind you where this is, it's stored under the name depth here. And you can see down here, I named this O2 at equilibrium, and this one I've named K gas X. So we're going to use those values later. The respiration rate constant for this formula here, the change in oxygen, is the minimum of the actual concentration of oxygen now, or this rate constant multiplied by the change in time. And why did I do this minimum function? Well, say that this function here predicts a concentration of oxygen that's greater than the present concentration of oxygen. Then that would result in a negative concentration of oxygen produced in the system using this model, and we don't want to do that. So the rate law actually is just KRS times delta T, but we want to say if that value is greater than the present concentration of oxygen, just make the whole respiration term equal to the present concentration of oxygen. That means that the system is going completely anoxic. Things are going to die. We're not going to explore scenarios where that happens, but that is something that can happen. So I just wanted to make sure that we don't blow up the model by having negative oxygen concentrations. Anyway, the KRS that was given in the problem was 0.00003 moles per liter per hour. So let's enter that in. Good. And again, I named this KRESP. And the last constant that we had was the K of photosynthesis, right here, KPS. And this is in units of moles per watt. So the amount of sunlight is measured in watts per meter. And so that unit is, or that number that we came up with is this number right here. So let's plug that into the equation. And again, this is a finite difference approximation that we're going to use. And so now we've put in all of our parameter values in different slots. And I'm going to make this one green. Fill that with green, because that is something that you can change. And now, this is just a way that I wanted to organize it so it's easy for you to see what values we're using. These are all the parameters that we're putting into the model. And now we have a separate spreadsheet where we're going to actually build the finite difference model. And here I have columns for time. And you see this is related to the time step, A2 plus delta T, A3 plus delta T. So each time it just adds whatever delta T you put right here. And we have a slot for the total concentration of oxygen in the system. We have this column for the change in oxygen over a given time step, so the big delta O2 due to gas exchange. And we're going to put a differential equation here. We have the change in oxygen over a given time step due to respiration. We'll put in a differential equation here. And the net irradiation, we're going to use that funny sign model to model. Then we have the change in oxygen concentration due to photosynthesis, which we need to base off this net irradiation value that we calculated in this column here. And then finally, we'll just sum columns C, D, and F to arrive at the total change in oxygen, which will then subtract from the current concentration of oxygen to arrive at the concentration of oxygen at our next time step. So let's go through and put in these differential equations. Well, first we'll start with the initial concentration of oxygen at time 0. And we named that, oh, we didn't name that. Let's say O2T0. Now it's named. And we'll just put it here, equals O2T0. And that fills in the value that we had. I don't know why it's auto-filling suggestions for me. It's almost never right. Now let's go here. What is a change of oxygen due to gas exchange? This, of course, we said was this formula here. The change in oxygen concentration due to gas exchange is equal to the rate constant multiplied by the gradient between the equilibrium concentration and the actual concentration, times the time step, divided by the volume. Or we can also say, as we just said previously, we can also say this is divided by the depth, because the top of the rectangular prism is 1 meter by 1 meter. So it's just 1 times 1 times the depth. So going back here, we can say that the change in oxygen is equal to K gas X, I think I called it. There it is. It pops up right there. Multiplied by the gradient. And the equilibrium concentration of oxygen, I think I called O2EQ. Yep, there it is. Perfect. Minus the present concentration of oxygen, which is in cell B2. Multiplied by your time step, call that delta T, divided by your depth, or divided by your volume. Yep. So hit enter, and there we go. We have a value for your first time step of the gas exchange of oxygen. Now let's put in the differential equation for respiration. We said, again, that this is just a constant multiplied by your time step. But we wanted to do that minimum function so that the consumption of oxygen could never be greater than the oxygen that's available in the system at any given time. So to do that, we said this would equal the minimum of these two values, the minimum of B2, or Kresp multiplied by delta T. And this is actually going to be positive, this formula right here. And so to represent a consumption, we just need to put a negative in the front. So there we have the negative respiration. And you'll recall that we were going to say that this is just constant, because organisms can't decide arbitrarily to breathe half the oxygen that they were breathing previously. And since the biomass of the system we said is not changing, this is actually just going to be a constant throughout the model, unless for some reason we drive the oxygen concentration down lower than this net respiration rate. Okay, so moving on to the sunlight model. You recall that we said that this was going to be equal to, let me just enlarge this real quick. We said that the sine function that we were going to use was sine of the time, which is in A2, minus 6, that shifts it so that sunrise is at 6 a.m., times 2 times 3.14, that's 2 pi, divided by 24. And again, this times 2 times 3.14 divided by 24, that shifts the frequency of the sine wave so that it repeats once every 24 units of time, or in our case, hours. Okay, so that's the sine function that we said we're going to use. But we said that we wanted to change the amplitude such that the amplitude was equal to the maximum amount of sunlight that would hit the stream, which we said was 3,600 watts per meter squared. So we're going to put a 3600 up front to change the amplitude or the height of the sine wave. And so this value will be in watts per meter squared. And then we said that we don't want the negative parts of the sine function. We only want the positive parts. And so what we can do is we can say max of 0, or this value. And this will return, oh, missing a parentheses. Dang it, foiled. Here, I need to have that there. Here we go. So it works. It should be 0 because we're at midnight, so there's no net irradiation. But then we also said that we wanted to add some random noise. And to do this, we said that we wanted between 60 and 100% of the sunlight getting through. And so to do this, to implement this, what we can do is we can say multiply this by a random number. The function for a random number in Google Sheets is rand between 60 and 100% represented as a fraction, or actually we'll just do it as rand between 60 and 100. And then we can just divide this number by 100 to get a random number between 0 and 1 that represents the fraction of the amount of sunlight that's getting through. And so here's our random cloud term. Here's the function that accounts for nighttime, the max of 0, or the sine function. And here's the sine function that accounts for the daily amount of radiation that hits the top of the atmosphere. And so if we hit enter, I hope this works. We can just copy and paste it and see if we generated some reasonable values. Great. You'll see that at 6 o'clock, the sun, it starts off at 0, so that's still modeled as 0. But at 6.5 hours, you have sunlight, which gradually increases till it reaches a maximum at 12.5 hours. Everything's just offset by a half hour because you're using the value at the present, or at the, yeah, everything's just a little bit offset. And then the sun sets at 1800 hours. So great, we have a net irradiation term here. This is a forcing that we use, and you can see it repeats every day. Night, day, night, day, night, etc., etc. And using this, we can now calculate the change in oxygen concentration due to photosynthesis, which we simply said, because biomass we assumed was going to be stable, and temperature we assumed was going to be stable, which are the two other factors that influence photosynthetic rate. We can say that the change in oxygen due to photosynthesis is just equal to KPS, our rate constant of photosynthesis, multiplied by E2, the sunlight coming in. And I'm just going to check to make sure. Oh, yeah, we just need a delta T multiplied by delta T. Okay, so that's cool. We've taken this radiation model that we just developed. It's really simple, but it's a working radiation model, and calculated the photosynthesis that's occurring at midnight, which is 0. Go ahead and figure. And so from this, we can now calculate the total change in oxygen over this time step from midnight to midnight 30, just by summing up these three equations. So we said that this equals C2 plus E2, or not E2, plus D2 plus F2. So there's the total change in oxygen. And here I just put a column to calculate the oxygen saturation, which we'll do. And that's just going to be the current concentration of oxygen divided by the equilibrium concentration of oxygen. This is just a convenient number to model or graph things with. So we'll say this equals B2 divided by O2 EQ. And let's multiply by 100 to get a true percent. So that's our percent oxygen saturation when we're starting off, 97%. Okay, now we've calculated this total change in oxygen over this time step. So now to get the change in oxygen for the next time step, we simply say this equals our previous time step's oxygen concentration plus the change in oxygen over the last time step, G2. And enter, you have your next step, next time step. Okay, we have completely set up the differential equation for one time step, and now it's just a copy-paste job. I'm just going to come over here, copy all these columns. Paste it into here. And now, I think we have something that we can copy and paste into every row. Just grab all these things, copy, moment of truth. Oh God, I'm so nervous. Copy and paste all this into there. And voila, we have a working photosynthesis model. Now, these numbers might not mean a lot to you, and that is totally fair. But let's plot it out. Let's see what it looks like. I'm going to go out of 200 times zoom just so you guys can see this a little bit better. Okay, we have time, oxygen concentration, and oxygen saturation over here. I guess let's just make a graph of oxygen saturation, insert a chart, stick the chart right here for convenience, I guess. Select our entire data range. I think it ended on row 242. So we'll say A1 to H242. Or no, 247, which it just suggested to me right there. Great. Oh, it populated with all these stupid series. Let's remove them. So we just have O2 saturation displayed. Oh, and I don't want a column chart, clearly. I want a line chart. Cool. Look at this. This is a dissolved oxygen model. It might not look too impressive from this perspective, but let's change around our axes. I think we can change this by going to vertical axis. Yeah, set a minimum of, say, 90. Look at that. So you can see here a nicely modeled oxygen dynamic for this stream. I'll put some labels on this later when I give you this completed spreadsheet, but I want you to fill it out first. This is our initial concentration. It was a little higher than it should have been, but that's fine. It drops down quickly. And you have these periods of nighttime. Then the sun comes up, the oxygen goes up, but it fluctuates because respiration is continuing apace, but sometimes some clouds pass over and kind of hobble respiration or hobble photosynthesis. So there's a little bit of noise. But every day you have this nice diurnal cycle or diel cycle of oxygen dropping down to some lower concentration at night. And it's constant down here because the gas exchange eventually equals the respiration rate at some point. So oxygen is entering the river as fast as microbes can respire it. And then during the daytime, you get this big bump in oxygen to even above saturated conditions. And down again during nighttime, up again during daytime. So voila. I think this is a pretty cool model to do in just a freaking spreadsheet. I want you to build this model yourself. And in the check-in problems, I'm going to ask you to change some of the parameters that we entered and see how those alter the rates of photosynthesis or the rates of oxygen change in the system. So I want you to be able to qualitatively describe how changing each of these parameters results in changes in the dissolved oxygen level. So I'll see you in class on Monday. Thanks for watching.